Hidden dimensions revealed. Linear algebra isn't just math, it's the secret language that powers machine learning, video game graphics, and quantum physics, as we've seen time and time again in this book. I'm excited to introduce a new playlist covering the appendix of this book, as linear algebra is a fundamental topic in the scientific community. If this interests you, be sure to hit the subscribe button for more. The full PDFs, as always, will be posted on Patreon and available to you. With that, let's jump into the first problem in this appendix. Alright, so in problem 8.1, we're dealing with vector spaces. And so we're trying to consider the ordinary vectors in 3 dimensions which have component x, y, z in the I, j, k hat directions with complex components. Okay, that's good to know. If their components were real or positive, integers, things like that, we'd have to have a little different criteria. Well, not really different criteria, but we'd have to handle it differently. That being said, part A wants to know, does this subset of all vectors with A sub z equals 0 constitute a vector space? If so, what is its dimension? If not, why not? Part B wants to know, what about the subset of all vectors whose z component is 1? Hint, would the sum of two such vectors be in a subset? How about the null vector? And then C, what about the subset of vectors whose components are all equal? That's an interesting one. Now, this is a tedious test of vector space axioms, and the goal here is to be aware of the forms of these vectors and whether they maintain the form throughout these tests. This is intended for those with little to no experience in proofs and axioms, so the work will be tediously detailed as such. So with that, let's start tackling part A with some definitions and see what our axioms are. Okay, so part A. We first have to define the vectors of the vector space. And to show that this is a vector space, I'm already giving you a foreshadow. We need to let alpha, beta, gamma, and the ket notation, since this is a quantum mechanics book and not the bar notation or vector hat notation like in linear algebra books, or even bold script. We're going to let these be in the space, but remember we define the space here in part A as everything that has a vector of last component 0. So we see we have some components here that are complex, 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 but 0 in the last spot. So any vector of these forms, we're just going ahead and labeling these 3 because of what's needed in the vector space axioms. But the whole concept here is that we need vectors, these column vectors of these forms with the last component 0. Okay, and the first of the big pillars of these axioms comes in from vector addition. So that is axiom 1. And what this property is known as when it's achieved is closure under vector addition, meaning that I take two vectors, I add them together, and I get another vector of the same form. That's what we have to test for. Now, specifically, this could be, you could generalize this in the abstract algebra sense instead of linear algebra and say that I want any two elements that are in the set of or collection of objects to be another element of it. So as such, we need to add together two vectors, why not alpha and beta? As such, what we witness here is that adding the alpha beta column vectors together, in this sense, we can add them component-wise, i.e. x to x, we see that there, y to y, we see that there, and 0 to 0, we see that there. As such, we know that since this is all in the x, we can relabel that as another component dx. Since this is all in the y, we can relabel that as dy. And then 0 plus 0, that's 0. And since I have a vector of x component, y component, and 0, that lives in the space, and we could say that we're closed under vector addition. And that's pretty darn cool. That's one of the first big pillars of all of these axioms, and we have 10 to go. Okay, so the next on this is called the additive commutativity, known as property 8.2 in the book if you're following along. And what we're trying to show is that does it matter which way I add two vectors? Does alpha plus beta matter or beta plus alpha matter? In normal numbers like scalars, complex numbers, real numbers, integers, it doesn't matter. So we're trying to show that in this case it doesn't matter for vectors either. So again, if we let alpha, beta be the two vectors of interest, we see here that by adding the two vectors again, we get this vector here that we saw last slide, and that we know that ax plus bx is equal to bx plus ax. And this works because addition of complex numbers is commutative and associative, so we're good to go. And so since we can apply this component-wise, then we can re-break this up into two individual vectors and recompose them and say that, yeah, we have beta plus alpha equals alpha plus beta, so we're good to go. So again, it's not really challenging per se, but it's tedious to get through all these axioms because we have to show that this element, which is constructed of individual components, everything works the way we want them to. The next, of course, has to be additive associativity. And so what we're really checking for here is, well, if I have three vectors, alpha, beta, gamma, does it matter which order I add two vectors first and then the third? So here, let's check it out. We see that alpha plus beta plus gamma, where we're going to focus on beta gamma first. We see we have the two vectors there. Add them together as you see here, again, component-wise. And then we get this other vector, which, again, all in the x direction, all in the y direction, and 0 in the z direction. So that does indeed live in our vector space. But does this equal the same as if I add alpha beta together first? Well, as you see, by changing the yellow parentheses and adding alpha beta first, we see that we do that here. We get ax, bx, ay, by, 0. Then we have the c vector here, which we add in component-wise. And as you see, comparing this one to this one, you get the same thing, and you're good to go. So far, we're 3 for 3 on these vector space axioms. So let's see what number 4 has in store. Okay. So here is where things start to get a little tricky because of the concept of additive identities and identity elements as a whole. So the additive identity explores the fundamental question, what element, when added to another, returns the original element itself? Okay, and we know that things like 0 are traditionally the additive identities for scalar addition, right, of complex and real numbers. So here, we're going to try creating what's called the null vector or the 0 vector. And we should take note here that this 0 vector, which has all components equal to 0, is indeed a vector in a space because the last component is 0, and that's really all we need to check for. So take a note of that there. Now let's see if we actually return the identity element if we add it, or the vector if we add it to this 0 vector element. And what we witness here is that if I just add alpha plus 0, just like we had previously in our other additions, we get to add 0 to each individual component of alpha. As such, 0 doesn't do anything under the complex addition, so we're fine. Okay, so we just return ax, ay, and back to 0. Cool. That keeps us in the space that we're looking at, and in particular, it returns to us the same vector. So this is good to go. We do have a null vector, we do have an identity element, and all we had to show is to make sure that adding the 0 vector doesn't kick us outside of the space. Okay, and we also had to make sure that the 0 vector itself lived in the space to begin with. We'll see why that becomes important here in just a moment. That being said, we also have to have an inverse. Now, in the traditional numbers, that would just be a negative number, right? Because if I add 2 and negative 2 together, I get 0. So the additive inverse is asking the question, well, what element, when added to another, negates it and yields the identity element that we had just shown above? Okay, so whenever we see the notation here, especially on vectors, it's important to note that the negative here or on the outside, however the text wants to define it, you're trying to say that every individual component in that vector is negated. Okay, and again, since we have the vectors of the form component, component, 0 in 3 dimensions, if we negate 0, we're still in the space, so this negated vector lives in the space too, and so we just take a note of that being 0, we're still good to go. Now let's see if it actually upholds with the axiom. So if I have alpha plus the negated alpha, which means I just add a negative to every component, then I can add them together. And by the way, here's another thing that is going around because of abstract algebra finals and things like that. All negatives are is just moving to the left of the 0 point on the number line. So when you see a negative, all it is the addition of a negative number. So the minus sign isn't really subtraction as we think, but the addition of a negative number. So little tangent there, Don. But nonetheless, it's still component-wise to component-wise. And then we see that AX minus itself gives us 0. AY minus itself gives us 0. And we end up with 0 again. Thus, the 0 vector is achieved, and we get the desired result. Okay, so we're about to take the step into the next big pillar of these vector space axioms with scalar multiplication. Emphasis on scalar. So just like scalar multiplication alongside vector addition forms the other crucial pillar in these vector space axioms. And just as vector addition requires closure, so does scalar multiplication. And this is because whenever I'm multiplying scalars to a vector, this operation essentially just stretches or rotates the vector. So a negative sign flips at 180 degrees. If I multiply it by a positive number that's greater than 1, I stretch it. If I multiply it by a number less than 1, then I shrink it. Things like that. So what we have to make sure is that that actually lives in the space too. Okay, and we see that in particular with relation to quantum mechanics, these stretch factors turned out to be the energy values because of eigenvalues and things like that. So we definitely want to keep that concept in mind, that we want to be able to live in the space of the energy spectra, so we have to have this closure property. So let's see how we need to do that. So this tells us that we need to multiply by some scalar number to the vector of interest, and we maintain the same form that we had. Since we know that the scalar out here can be multiplied component-wise by definition, we're good to go. Because then we just have a times ax, a times ay, and a times 0. But a times 0 yields 0. These other two yield some unknown form, but doesn't really matter because we maintain the form of component, component, and 0. Okay. So that does live in the vector space, and we're good to go. This is really crucial, and really, if you want to test A1 and A6 first, you're pretty good to go there. Also, this additive identity often fails a lot because what happens if I have numbers that are just supposed to be positive, then I fail because I don't have a 0 vector. Similarly, if I'm positive, then I don't have negative numbers in my set, so I can't construct a vector. So very important to us. But one of the things to note that I didn't pay attention to the first time I took linear algebra years ago was scalar multiplication is about all we need, because vector multiplication or matrix multiplication is not really well defined in terms of space properties like the algebraic rigours would want. And so many have said that that was just an ill-posed definition and idea because you have things like dot products, cross products, and other operations on there that could be used. So all we need is scalar multiplication, which really makes this a lot easier. All right, now we're getting into some properties that we love to have. Now, upon scalar multiplication, we also have scalar multiplicative distributivity, and this is the first one, which is known as the linearity property, meaning that if I have a scalar on the outside of two vectors, right, I can distribute the scalar to both of them, and that's what we're trying to show. Does it actually work? Well, if I add the two vectors together, like I see here, then I get this conjoined vector here, but I have a scalar outside, which I know I can multiply component-wise. Now that I have it on every component, I'm good to go to multiply this into each individual component in the curly brackets, as we see here. And note that doing this upholds the same form because I get a times 0, and then I have all my ax's, ax, ay, 0 here, bx, by, b0 here, which I can now split that up. Okay, now after splitting it up, I could refactor the a outside, and then I get to reconstruct my alpha and beta vectors in the same way. So what we just showed is that this acts exactly how you'd want it to act. I just need to make sure that I put it on the left side because, as we saw in the quantum mechanics book over and over again, oftentimes these things have other things attached to them like operators and things like that, which is left side, right side dependent. So you have to be careful on which side you're distributing or which side you're factoring. That leads us to the second distributivity law, where I can distribute over addition, meaning that instead of having two vectors, what if I have two scalars added together? Now, if I have two scalars added together, of course we just go ahead and find out what the new scalar is and see if it's within our working set. Or I could just go ahead and prove that using the same idea here. I could take this, multiply it to every single part here, and now that I have it on a component-wise basis, I can distribute this component into both parts here. This component to both parts, this component to both parts, and now I see I get a fully expanded and distributed form. And now I can go ahead, split it up just like we saw in this step. But here I have two scalars here, so not two vectors. And then I can go ahead and simplify that down. Easy enough. Now I see I reconstitute after factoring, factor the b out, and then I can plug in my definitions for alpha alpha, and I'm good to go. So either way, both of these are pretty much exactly what you want. They're just kind of tedious to show that it works. Because again, sometimes there's weird number sets and weird implications, but it is what it is. Not too bad, just tedious. All right, home stretch here. Let's just see. All right, so we still have to see if the scalar multiplication is associative, and I think you can see what's going to happen here and why it happens so fast. So much like we had with the addition being associative, doesn't matter if I multiply b to alpha first and then multiply by a or not. So if we go ahead and put our orange or yellow parentheses here, I know that I could focus on b and alpha in component form, distribute that in, component, component, component. Then I can distribute a on top of that, and we see that it doesn't matter. I still get the same AB combination on every component. With that AB combination, I can go ahead and regroup them in my yellow curly brackets there, factor them out. Now I see it's the same thing as AB times the vector itself, which goes back to there. So yes, we're good to go. Scalar multiplication is associative, so we have the nice properties in the landscape of algebra that we want. Now, just like we saw with the additive identity, we need the multiplicative identity that returns the vector when multiplied. So the concept here is that we need the scalar multiplicative 0 and identity. So if I take 0 and I multiply it by the vector, do I get the 0 vector? Well, yeah, because if I take 0 here, I need to distribute that to every single component. 0 times every component leads me to 0, leads me to the 0 vector. So we're good. Same thing. Here's the multiplicative identity, and this one also fails a lot. Do I get the same vector back when I multiply by 1? And as you see here, I have 1 times our alpha, and then I say I can do this component-wise. 1, 1, 1 times every component, which just returns my components, and I'm good to go. So I have closure under this multiplicative identity too. That being said, since we didn't have any problems here, the given vectors indeed constitute a vector space, and we have fulfilled all necessary vector space axioms. Now, this vector space is only two-dimensionals. Why is that? Comment below, and don't forget that the full PDF is on Patreon with the explanation as to why and what it represents geometrically. Now that we've seen how to kind of cruise through this and what to expect, we're going to kind of blast past the next two parts of this question so we can get this done in relatively quick time. But again, for the intended people or the intended audience of those who haven't seen this stuff before, going a little slower and step by step, I find it incredibly valuable. And once you see it once or twice, then you're pretty much good to go. So let's go ahead and move on with this and see what B has in store. So in part B, we had a different definition, right? Because we wanted that last component to be 1. Now, this set fails, and I'm already giving you the precursor to what it fails for, but take a second now to think about why it might fail based on the given hints and based on what we just saw. So if we want to define the space where alpha, beta, gamma, and any other vector has the form where we have 1 in the last component, this is what all our vectors would look like. Note we have 1, 1, 1 here. Okay, so if we just attribute to the first hint that they gave us and check out the vector addition, are we closed under this? If I add alpha, beta together, do I get another vector of the same form? Well, as it turns out, we don't. because if I look at these vectors and I add them component-wise, x to x, y to y, z to z, 1 plus 1 gives me 2. And this 2 throws it all off because now I don't have a vector of the form with 1 up here, right? I see I have 1 in all my last components. This 2 here makes it to where that's not 1, so I can't be in the space and I fail, okay? Not to mention that if my last component is 1, that means I can't have a 0 vector there because 0 would not be in the set of vectors to choose from. So I fail another vector axiom, okay? So this set of vectors fail to form a vector space due to multiple violations of the vector space axioms. Primarily, the null vector is absent from this set because its last component is 0, not 1. Furthermore, the addition of 2 vectors in this set produce a result with a last component of 2, which falls outside the defined form, violating the closure property, as we see here. So while a single axiom failure is sufficient to disqualify a set as a vector space, recognizing multiple failure points provides valuable insight into the nature of the abstract vectors and their associated spaces. Again, if you can so you don't want to go through the whole checklist every time. So if you can kind of see where things might fail quickly, that's where you want to go to. All right, now we can get on to part C and run through this. This one's actually a really clever one, and I'm kind of excited to talk about it. So, to show that this is a vector space, because of course the author's not going to just give us one vector space and not another one, we need to define the vectors, and the vectors that he told us in the question needed to be defined such that every single component is equal. So ax, ay, az all go to A1, bx, y, z all go to B1, and cx, y, z all go to C1. That tells you that every component in each individual vector are even. Now that we have that, let's check and see if we're closed under vector addition. So what do you think the instinct here is? Because this one is non-intuitive at first, but then it becomes apparent. So as we see, adding two vectors component-wise, we see that every single one of these components is equal. So if we relabel them to D111, then we see that since they're all equal, we live in the vector space and we're good. Okay, this is what we mean by we have to look at the form specifically. We don't really care what you call it, but sometimes relabeling it helps make it clear. But we need to look at the form, and if every single component, regardless of what I add, multiply, etc., do to it, then I'm good to go. Now, moving to commutativity, we see that A alpha plus beta here, because I could switch them in this step here due to addition being commutative, I'm good to go. So I can reconstruct my vectors, no big deal, we're good to go there. What about associativity? Just like we saw in part A of this, it doesn't matter because we're adding and we're good to go, and adding component-wise is the same as adding numbers, so we're good. We see, again, every single component is equal. Does this work when I put the parentheses on alpha beta? Yes, it does. Every component is equal, and this is equal to this, so we're good to go. All right, part C with A4. Now the identity, this is where we have to do a little more talking. Because we redefined what the form was, such that the form had to be all equal parts, well, 0, 0, 0, they're all equal to one another, so that does lie in the space as well. So, as we see, we get every single component is equal. In particular, it's equal to the same thing that we had, so we do indeed get the identity element. The inverse, same thing. If I negate every component, if I start it the same, when I negate it, it still stays the same. It was just all with the negative sign, so we're good to go. And now we see that we have alpha and then negative alpha, add them together, we get the 0, so we're good to go. And we see that again, making sure that the inverse vector and the null vector are in this space, very important to check off too. Of course, now we need to see if we're closed under scalar multiplication. And of course, if I multiply everything to component-wise, I get a new component, but since every component's the same, I'm good to go. All right, coming down the pipeline now. What about distributivity 1? Well, just as you would probably imagine, it all works out the same. alpha with AA because I can add them together, same vector, good to go. Split them up, checks off. What about distributivity over addition of the scalars? Yep, that works too because I could distribute each component to each part of that scalar. And so I do indeed go back to the form I need. So we're good to go there. Okay. Now finishing up, we see that scalar multiplication is indeed associative, so we're good. Doesn't matter, just like we had saw last time. Again, the big thing here is just to make sure that when you get to this step, right here in the middle, if that does not have every single component the same, then the vector falls out and we don't have a vector space. But now that this component does exist in the space, we know that scalar multiplication, we can just tidy them up together, factor them out, and we're good to go. 0, well, we know that a 0 vector does live in a space, so we're good. So a 0 scalar can also make that happen because 0 multiplied to each component here brings me to a 0, 0, 0. So since that 0 vector lives in my space, I'm good to go. Same thing with my identity. If I multiply 1 to everything, I still get every component equal to the other components, so I get my vector back. My vector lives in the space, so we're good to go. So this does constitute a good vector space. But what makes this vector space different from the one that we saw in part A? Okay, this one only has a dimension of 1. Where exactly does that lie and what does that tell us geometrically? That's a good insight to think about because when you know that you have one-dimensional vector space, then what you could ask yourself are things like, well, what about the span of all the other vectors, linear combinations? Where would I expect to find them? More importantly, as we saw throughout quantum mechanics, we needed more important things like eigenvalues and eigenvectors. But if my vectors only have a one-dimensional vector space, then what happens? That's what we have to be aware of. All right, that was really fun. Holy moly. So if that video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment now to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey, especially trying new things like we are now. And if anyone else is interested in joining and supporting the channel and joining our Patreon community, you can check out the description and the link below. Together, or the link in the description below, can't read now. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.